So just before I begin, I wanted to get an idea of who here has used Go before. So can you just put your hand up if you've used Go? All right. So I was going to just give a talk that is this one, which is a pretty technical talk about what is changing in Go in the next release. But I feel like if the majority of the audience is not that familiar with Go, perhaps I should give some introductory material as well. Put your hand up if you're interested in sort of a brief introduction to Go and some stuff like that. All right, so I'll do that for sure. So I'll just start by saying like what Go is. Go is a language that we started developing at Google about 6 years ago now. It was really motivated by our needs at Google as a company. And you know, we needed something that was efficient, safe, concurrent, all these kind of things. But the most important thing is that Google operates at this really large scale. We have many thousands of programmers working on hundreds of millions of lines of code and deploying that code to many, many servers all around the world. And there was no language that was designed with that kind of scale in mind. There are languages that are designed for ease of use, like Ruby, for instance, to be flexible, to be easy to work with. And there are languages that are designed to be very efficient, very close to the machine, and so on. But none that really took into account many people working on code bases together and collaborating. And so the sort of key tenet of Go's design is that it's very simple and lightweight and easy to understand. And one key part behind that is that the design process was driven by consensus. There were 3 people, Rob Pike, Ken Thompson, and Robert Griesmer, who over a period of, I guess, 2 years, put together the original language spec. And they didn't put anything in the language unless all 3 could agree that it was the right thing to do. And as a result, the spec is very short. It's something like 50 pages if you print it out. And if you know these 3 people, you'll know that they're all very different kind of people and have very different technical opinions. And so it's a surprise that the language exists at all, in a way. But so as a result, the language is this kind of lightweight language. It feels like a scripting language. It's very object-oriented, it's very heavily object-oriented, but it's not object-oriented like you would imagine. You probably think of something like Java or Smalltalk or something when I say object-oriented, but Go is not quite like that. It's a concurrent language, so it's designed for the modern world where most processors do many things simultaneously, and so it gives a lot of language support for concurrency. And it's designed for working programmers. It's not a theoretical language, it's not experimental. It's quite different to most languages, but it takes a lot of existing ideas. So it's not, it's just designed for software engineers, not for language theorists. So in March 2012, we released Go version 1, and that was after Go was released as an open source project in November 2009. So something like 2 and a bit years after the release, the initial release, we have Go version 1, and the most important thing about Go 1 is that it is a standard of the language and the libraries. So if you write code for Go 1, it will compile and run in exactly the same way under Go 1.x. And we think that the Go 1 line will continue on the order of many years, where we have issues in our issue tracker marked as Go 2, but that doesn't really mean that Go 2 is happening anytime soon. So it's been a really great thing. It's the best move we made as a project. The stability means that there's no version skew in the community. It means that everyone is working with the same basic tools and libraries and so on. And it just makes it all a lot easier. So this is some Go code. It begins with a package statement and an import statement. So I'm importing this package called funct. And then I have a function, a main function, where I call a print function in that main function. I can run it, and you see what you would expect to see. So I'm not going to sort of go through all the different aspects of the language or libraries. I'll just talk about a few parts of the standard library. And to understand the standard library, you just need to understand packages. All Go code lives inside packages, so a package is like a unit of Go code. And inside packages, you have several, or even as few as one, but one or more like type, function, variable, and constant declarations. And packages can be really small. Some of them just have just one thing in them, or very, very large. So, but most are somewhere just in between them. And as a result, it's not, you can sort of be as granular as is appropriate when you design packages. One really notable feature is that the case of your names determines the visibility. So you don't have a public and private keyword. Instead, you export things from a package by giving them a name that begins with a capital letter. And the really nice thing about that is when you read a piece of code, you immediately know, just looking at the names, whether it's part of a public interface or part of the private implementation. And that's an example of one of the features of the language that makes it easier to work at scale. When you're reading some unfamiliar code, just looking at the case of the name makes it a lot easier. For instance, when I look at C++ code at Google, you're looking at some big class, and there are just names referenced in the code, and you have no idea whether it's, you know, a public, private, variable, function, whatever. It could be anything. And that's just not the case in Go. So I mentioned that Go is really object-oriented. The key of Go's object-orientism is its system of interfaces. And so in Go you have interface declarations that contain a set of methods. They're just method signatures. And then any type that implements those methods is an implementation of that interface. So you don't explicitly say, my type implements foo. If it implements that method, then it is that foo. And so two really common examples of interfaces in Go are the I/O packages, writer and reader interfaces. And they basically define readable or writable sort of streams of binary data. And so they specify these write and read methods that take like a byte array and return the number of bytes that have been written or the number of bytes that have been read and an error value. And there are many, many implementations of these read and write methods, these reader and writers in the standard library and in other code everywhere. Basically anything that passes streams of data around will implement one of these. And so to give an example of some of those in use, this is an example. Can you read this from over there? It looks pretty small. I can barely read it from here. This is an example of using a few different types of reader and then chaining them together. So we start by declaring this IO reader variable R, and then I use this string, this function from the strings package called new reader, which takes this data string, this is just a string constant, and it returns a reader that will emit that string when you read from it, and you call the read method. Then I create a base 64 decoder that wraps that reader R, and then returns another reader that base 64 decodes the input and yields the decoded data as another reader. So it's kind of like a Unix pipeline. Then I create a gzip reader to wrap that reader, gives me another reader, which I then copy. I use this IO copy function to read from that reader and write to this writer, which is the os.standardout. That's the file handle that is standard output for this process. So basically, all this code does is base 64 decode and then gzip decompress this string and print the result to standard output. So if I run it, you can see it's a little poem. But that just kind of demonstrates this sort of generality of readers and also the ubiquity of those interface types. Go's standard library also includes a HTTP server and client that are really high performance. This is just a really trivial example of a web server where I'm creating this type greeting, which is a string type. And then I give it this method, serve HTTP. So that's the method receiver. And its arguments are a response writer, which is something that I write my HTTP response to, and a request, which has the details of that request. And I use fprint to write the greeting string to as the HTTP response. In my main function, I set up a web server using the listen and serve function, listening on port 4000, that creates a greeting value and uses that as the HTTP serving object. So when I run this program, it's started a web server listening on my machine, and if I go to localhost 4000, I get that greeting message displayed. And so a really important thing about this HTTP package is that it's a really well-tuned, high-performance, DOS-hardened web server. It's the same web serving infrastructure that serves dl.google.com, which is the site that serves Android and Chrome downloads and all of the big binary downloads that Google provides. So they're all served by the same stack that you can use yourself. And so you don't need to put this behind Nginx or some high-performance web server. It should be equivalent for all intents and purposes. JSON encodings in the standard library. There's some other stuff. I won't go into all of that. But I'll talk a bit about the tooling system. So, the Go tool is the standard for building and installing Go code. So, when you install Go, you have this Go tool, and it has all these subcommands. And so, you can build with it, obviously. You can install. You can also inspect like packages that you have installed. So I can, list all the packages on my system, which is, I guess, a lot. But there's a lot of stuff there. And I won't talk about that. You can also use it to fetch remote repositories. And an interesting property is that Go's import path, so this is the import statement you would use in some code. You actually use the URL of the repository as the import path. And so you can fetch remote code by saying go get to fetch that. Or if you fetch a package that has other remote dependencies, it can fetch them recursively because all of the dependency information is inside the program itself. So that's a nice, and also it leads to other nice tools. So if I'm interested in the WebSocket package documentation, I can go to godoc.org/that import path, and this site godoc.org will fetch code from the remote repository and read the documentation out of the source files themselves, and then display it on the screen. And I'm actually getting a little bit ahead of myself here because I haven't talked about documentation. So the GoDoc tool extracts documentation from Go code itself. And if you've used PyDoc or JavaDoc, it's kind of similar. The main difference between GoDoc and those tools is that the comments are just normal comments. They don't have some kind of prescribed format. There are some very small ways in which you can do some formatting of those docs. Like if you indent the comment, then you can have like a section of fixed width text. But otherwise, it's pretty much just as is. And so basically, if you have this function declaration split and this documentation, it comes up on the web page as something like that. And it's also available. I can look at this string split documentation there in my browser. And because my window is not as wide as a punch card, there you go. But the really nice thing about this is that documentation that lives alongside the code is easy to keep up to date. And as a result, things tend to be well documented, if they are documented at all. So one of my favorite parts about programming in Go is the Go font tool, which is a pretty printer for Go source code. All of the Go code in the core is run through this tool. All the Go code we write at Google, and pretty much any sensible Go programmer runs their code through this tool. And as a result, nobody talks about things like indentation or brace position or any of those really tedious topics. Instead, all the decisions have been made already and they're enforced by a program. And so, to give an example of it in practice, you can write a Go program. Oh, I already have hello.go. So, if I have this all kind of messed up,
Put some spaces before fuck.
yeah, some crazy, whoa. And then I have it actually hooked up to save in my editor, so whenever I save it reformats it, runs through GoFund. So when I save that, two interesting things are going to happen. One is it's formatted it properly, but I'm also using something that Brad wrote, which is a extension of GoFund. It's called Go Imports, and it not only reformats the code, but it also looks for usages of packages, and it will actually walk my source tree and find a package named font that has a type of print line and add this import statement to my file. So, if I say strings.join,
Print that.py.
is that not fine? It adds the strings method as well, strings import as well. And this is really great when you're working on code and iterating fast, because not only do you not have to remember to add the import statements, but in Go, the compiler will actually give you an error if you import something and don't use it.
That's also the view.
Yeah. So if I delete that, it'll go back to the way it was before. And so if you're like adding print statements to your code to test something, it will automatically add the func package, and then when you stop, it will remove it. And so you don't get the compile errors, which is great. And I can test that.
It's not just them.
No, it's not Vim. It's not just Vim, it's Emacs, whatever. It's just a command line thing.
What's the name of the tool again?
Go imports. And you can install it by typing go get. Whoops. Like that. And if it wasn't already installed, that would take a few seconds to check out and then install. Cool. The Go tool also provides some testing infrastructure. And it's a really lightweight testing infrastructure, but it's been widely used and seems kind of a really nice balance. Basically, you just write, packages consist of multiple files, and usually those files are all just compiled together into the one package namespace. But if you have files that end in _test.go, those files will not be compiled when you normally build, but when you run a test, they'll be compiled in. And any functions in those files that begin with capital T test and then some other capitalized word will be executed as tests. And so this is actually a real test that's been truncated a little bit from the strings package, which is testing the strings index function. That's a function that locates a substring inside a string. And so we just have this like table of tests, which is just a array of structs in Go. And so each one has an input string, some substring to search for, and then the returned index of that string, or the expected output. And the actual executor is just a for loop iterating over those tests, actually calling the string's index function, and then comparing the output and then logging the error. And so the test is just totally all Go code. It's not in some kind of meta language or domain-specific language. And so in this case, I'm sure you can imagine or think about some other test framework we've used that would be much more concise to do exactly this. But as soon as you need to do something a bit more interesting, you have the whole Go language at your disposal, and it's all very obvious what it's doing, which is a bonus. And so executing tests is really simple. If I'm in the strings package, I can say go test to run all those tests. And it ran pretty well. If I run it with -v, I'll see all of the tests as they're running. That's quite nice.
This is so slow.
Why is it so slow?
The startup.
I don't know. Because my machine's slow.
Go test -i. Did you have things not installed?
No. Anyway. The testing tool also has benchmarking facilities, which is really nice. And so if I want to run the strings benchmarks, which I guess would probably be a bit slow, you'll see. And that's convenient. And there's also tools to take this output and run it against the old version and then compare versions so you can see the speed up between the old and new versions. And another thing, a feature that I really like is executable examples. So in your tests, if you have functions that begin with the word example, they will actually appear in Godoc as executable example functions. So for instance, this is from the strings package again. It's example index. It shows how to use the index function. And if I look at the index example in Godoc, it actually includes that example code, and I can run it and play with it and see if, see how it changes, experiment, and so on. And when you run your tests, so if I look at when you run the tests, it will actually execute this function and then compare the standard output that's produced while running that function with this comment. And so you can document and test your code simultaneously, which is a pretty nice property. All right, and there's a lot more. One of the things that was added in Go 1.2, so now I'm sort of turning into the talk that I said I was going to do, is coverage profiling. So I can run the tests for the strings package and create, if I do write -cover, it will actually, it's pretty clever, but it's telling me that 96% of the package is tested, so it's a pretty well-tested package. The way it does that is kind of clever. It actually rewrites the entire package source and installs counters before and after each statement in the entire package. And then it executes all the tests, and then it extracts all the counting information. And because it does it like that, you can actually write coverage profiles. So I can create a coverage profile called cover profile.out, and then I can run the cover tool to examine that that file. So how do I run it again? Whoops. Oh. Yeah, so I can get it to tell me all of the functions and which ones are tested and which ones aren't. So I can see that the toTitle case function is not tested. So this is a pretty boring package to be testing, really. You can see that the explode unexported function, some part of the implementation isn't tested. But this is kind of an annoying way to be looking at this. If instead I run with -html, it'll actually generate a report in HTML, and I can see that all of the red statements are not covered. Right, so there's a few error cases that I'm not testing, and so I could update the tests and so on to reflect those. So that's new in Go 1.2. But there's also memory and CPU profiling as well. I guess I could run one of those.
Lock contention profile.
Oh yeah, there's lock contention profiling. So that's an interesting one. If I run what is it? What's the flag? You've used it more recently than me. Block profile.
Block profile.
So it's go test block profile block, and I'll do it on the HTTP package because it's a networking package. Does a lot of things concurrently, and we can get a blocking profile for that.
Probably only one more test. No matter how long it'll take.
Oh yeah, it's actually going to be pretty slow.
Let's see.
Maybe I should. Which test should I run?
Benchmark client server. Just say run none and then say dash benchmark. Dash benchmark goes client server.
What am I doing wrong? Package dog. Is it just dash bench, isn't it? Alright, so I'm just running one benchmark with the blocking profile enabled. And then how do I turn blocked it out into...
Go tool prof, and then http.test, and then... And then the block that out. And type web.
Yeah. Oh no. Thanks Illustrator. Thanks Adobe. Alright, so it's generated this nice little graph, and I'll just tell Illustrator to fuck off. I mean, it's a video camera. Great. I hope they're watching. Don't steal SVG. And so if we zoom in, we can see a graph of where everything's blocking. And so the bigger boxes are the things, so you can see that it spends 6% of its time waiting for channels, 92.6% of its time in select. I actually don't know what to make of this. It's pretty well tuned, so that's kind of what you would expect.
No, I mean, that's like the client waiting for the server to reply. So.
Yeah. But this is really invaluable when you're trying to figure out what your program's doing, and particularly if you have a program, a complex concurrent program that is hung in some particular state. Coverage profiling can tell you like why it's blocked. Otherwise, you would need to kill your program and get a stack trace and examine the stack trace. But if you have, say, like many hundreds of thousands of Go routines, it can be kind of painful to try and figure that out. So this makes all of that a lot simpler. And like I said, you can get exactly the same kind of graph for CPU usage and also memory usage. You can see which parts of your program are allocating and so on. And when you're tuning code, it's just totally invaluable doing that sort of stuff.
Can you actually use this in a regular application, or only when you run this with, a memory profile and CPU?
You can attach to a running program and get information from it.
Yeah. Yeah, I mean, it's not, you need to put the profiling hook as an import statement in your program. So it's not as seamless as the testing stuff, in which it's all built in. But yeah, you can.
It's basically a one-line change, and then it has an HTTP handler that exports the data.
Those are rabbits. No talk of mine would be complete without rabbits. Okay. So anyway, Go also has debugging support. It has this thing called vet, which is kind of cool. It analyzes your code for programmer mistakes, so not compile errors, but things that are probably wrong. For instance, if you use printf and you have mismatched arguments to the formatting string, it will notify you of those. If you try to put a formatting string and you use print line instead of printf, it'll tell you that. It'll also warn you if you commit some of the more common kind of programmer errors and so on. There's a long list of things that it does now. All right, so that's Go. There's a lot more going on. I haven't even talked about the concurrency support or anything, but it's all pretty awesome. I was kind of starting to hate programming. I think every programmer has this kind of oscillation between really loving programming and then you sort of get really good at things, then you kind of hit some wall somewhere, and then you kind of go down into this trough of hating programming. And for me, it was like every sort of 2 years, I would kind of just go from hating it to loving it and so on. And I was kind of in a hating it mode before I discovered Go. And I've kind of been loving it since then, and I haven't gone back down, which probably means I'm heading for like a really bad downer in a few years' time. But at the moment, I'm having a great time, and it's been 4 years for me. And I just think it's amazing. Go 1.2 is the third major stable release of Go. It came out in last year, in December 1st last year, and it was mostly it included that. It included that test coverage support that we looked at. But it was mostly changes to the implementation, optimizations, some very, very minor language changes that aren't even really worth discussing here. But mostly just fixes and tightening of screws and so on. 1.3 is probably going to be a little bit more interesting, but again, it's a lot of behind the scenes kind of stuff. The code freeze, so the way we develop, the cycle of development that we do for Go is we sort of have like 3 months of development or 4, and then we have like a code freeze. It's not like the code is frozen, it's just no new features can be done, no sort of stuff that might break something can be done. And then, so that's going to happen on March the 1st, and then our release is on June the 1st, which I thought we were going to shorten the freeze cycle this time.
I like your mix of date styles.
I think it will change a little bit. Oh, I'm mixing date styles, right. This is what happens when you're an Australian that works for an American company and you have to like shift your conventions all the time. Sorry. But the idea, we're trying to move to a 6-month kind of release cycle. Oh, and when I say we, I don't think I mentioned that Go is an open source project. There are several hundred people that work on Go, and like about a dozen of those work at Google. So it's very much the community's project as much as it is ours. And we have a lot of really great contributors from all over the place. So that's a really great situation to be in. So Go 1.2, as you saw, was largely just all these kind of miscellaneous things. So we thought for 1.3 we should plan it a bit more, and so we created a document that we compiled with all the things that people wanted to work on, or were working on, or are going to work on. And so we have this kind of aspirational list. It's not necessarily everything that will happen, but it's things that we hope will happen. And so I'm going to just talk about those things. The first thing is we now have an 100%, for all intents and purposes, precise garbage collector. So previously the garbage collector was conservative, and so there were some pathological cases, generally on 32-bit systems, where you would have some data on your stack that looked like pointers to data. And so some memory would get pinned as being used when it should really be free. And so you would have these kind of slow memory leaks in certain programs, and it was very unpredictable. And that should just not be an issue anymore as of the tip of the current tree, which is great. So one, in a related sense, one of the big changes in 1.3 will be a change in the way stacks are managed. So in Go 1.2 and earlier, Go's stacks were split. So you would have, when a Go routine, which is like a thread, is created, it would be, say, 4K in size as its stack. And then as the program needs more stack space, you would allocate additional segments of the stack. And so there was basically just like a linked list of stack segments. But there were these problems where these kind of pathological cases where, say, you have some inner loop that does some small stack allocation, puts more things on the stack, where the stack would grow just past the segment boundary, and so you would allocate a new stack segment, and then it would, in another part of the loop, it would deallocate that, and so you would be doing this allocation, deallocation inside some inner loops.
Like the JPEG decoder.
Yeah, like the JPEG decoder, and you would make some kind of unrelated change to some library code, and it would just like tip the stack size over some magic value, and then suddenly your loops get really slow and you're not even sure why. And so in 1.3 we'll be changing to contiguous stacks or copying stacks, where when the stack needs to be grown, we just copy the full contents of the stack to a new larger stack segment, rewrite all of the pointers inside that stack, and then continue executing. And so that solves that hot split problem and shows some nice performance benefits. So this is some initial analysis by one of our engineers who is implementing this. And he just played with different stack sizes and showed the existing segmented stack approach compared to the contiguous stack approach. And you can see this is doing some JSON decoding. And this is the number of megabytes per second of JSON data being decoded. And you can see that the old approach is consistently slower than the contiguous stack approach. So it seems like a real win. A lot of the work is already done. Is it finished yet, or is it? No, it's still ongoing. But if you're interested, I've got these little links throughout, and these link through to these design documents, and so you can actually read like probably way more information than you're actually interested in about how all this stuff works. But it is actually very interesting. Okay. So another feature that will hopefully make it into 1.3 is the pool type in the sync package. And basically, this is addressing a common problem that a lot of Go programmers have, which is they have some kind of object. So you have a package that has several users or whatever, and you need to allocate like several of these objects, use them for a little while, and then you don't need them anymore. But they're basically interchangeable. So you would end up keeping a kind of free list somewhere in your code, and this is a free list that uses a channel for thread safety, and it's just like a little buffer of these objects. And so when you want an object, you would call this function object, and it would try to see if there was something in the pool, and if there is, it'll give you that one that was created earlier. But if not, it'll create a new one and give you the new one. When you're done with the object, you would put it back into the pool with a function like that, and that would try and put it in. If the pool is full, it just throws it away. And so, you would be you'd be getting an object, using it, and then putting it when you're done. And so a common one example of that is in the HTTP package. We use these buffered reader types to conveniently read data from a reader. And they contain their own little internal buffer. And so we had a free list just like this to keep instances of those buffers around in between HTTP requests instead of reallocating all the time. And so this kind of thing would just crop up in a lot of places as an optimization, just to take pressure off the garbage collector. But what the sync pool type does is it gives us a general case, thread-safe free list, which is not very interesting in itself. What's interesting is that it is the Go runtime and the Go memory manager is aware of this type. And so it's, when it does a garbage collection, for instance, it can automatically purge all of those things in the pool. Whereas before, you would have these tiny pockets of allocations that would just never go away because you have these free lists that are always keeping these objects in memory. And so the pool just gives you a way of, a convenient way of building these kind of pools, and also a way of just flushing that data out when it's no longer needed. I say it's an experimental type and might not be needed. Who would see themselves using this? Is there anyone here who has a use for it? So if you do, you should, there's an issue, do they bump the issue? I don't know, how do we get people to vote for it?
Star it.
Yeah, if you find the issue on the issue tracker and star it, there's a greater chance that it will be in, or even leave a comment, whatever, say I would use this. Because we're sort of collecting data on how useful it would be. Yeah.
Isn't this sort of, how do you call it, not enigmatic, as in you're manually managing memory?
Well, so Go is the garbage collected language, so you can just not manage memory at all. But the way a lot of parts of Go's design give you direct control over allocating memory and, you know, passing things by pointers or by values, and the way slices work and so on. All of these things make it easy to manage memory in some way. So it's not true that in Go you don't manage memory. And it's not unidiomatic to avoid allocating where possible. Certainly it would be wonderful if you know, you could just allocate and the garbage collector would be perfect and everything would be fine. But when you pass that work onto the garbage collector, the work doesn't go away, it just goes into a different place. And, you know...
I mean, often we write code and then we look at the CPU profile and it says, you know, we're spending 35% of our time in GC. And then we, you know, instead of typing -CPU profile with GoTool or whatever, we type mem profile. Then we see all the places that are allocating memory, and we see like 85% of our memory is coming from this one line here where we're making gzip readers every time, and inside of that is a plate reader, inside of that is a 1 meg buffer. And so every little request, we're just making 1 meg and throwing it away. And so then once you look at a profile, you're like, okay, maybe I'll reuse this 1 meg buffer every time. So, I mean, it's really something you do after the fact.
Yeah, you certainly wouldn't go into it thinking, I'm going to use a pool here. And you certainly wouldn't use it like you would use it in like the 1% of cases, right? So that's why there's a question whether it should be introduced or not. Because, and if you look at the documentation for it, so you'll see that there is a big comment that says the intended use is for this, and you know, an example of like, if you know, that's a bad use of it, don't do that, and so on. So we're trying really hard to not make it something that people reach for as a general tool. It's very much an optimization. Cool. So Go 1.3 will include a native client port. So native client is a technology, an open source technology that was developed at Google to sanitize and allow the execution of untrusted x86 code. So if you compile something with the native client compilers, well, they're like extensions to compilers, you get a binary that can be verified to only make special native client system calls. So the only interaction it can have with the outside world is through a trusted API, and you know that it's not doing anything else. And so the original target for this technology was to create like Chrome extensions and websites that could serve you just a big blob of a binary executable, and you could safely run it from inside your browser. And this is now shipping in Chrome, but it's switched off for everything but the Chrome Web Store. It's on now, generally? Oh, wow. So now you can write a web page that is a real program and have it execute on real systems. So that's kind of cool. but we've written, the NACL toolchain also provides a tool just for executing command line binaries. And so the Go 1.3 NACL port targets that tool. And it runs on 32-bit and 64-bit systems. There is an ARM NACL version, but we're not targeting that right now.
The other thing, we don't target Pinnacle, which is what Chrome runs.
No, but there's so I didn't want to talk about Pinnacle, but there is an ARM thing that's like the 32-bit. Anyway. But we're currently using the NACL toolchain in the Go playground, and for those of you that haven't seen it, the playground is just a pastebin kind of site, except you can also execute those programs, and it sends the program to Google servers, and we compile and run the program and then send the output back. So obviously we can't just run anyone's code in an unsafe way. So we use the NACL toolchain to sanitize the output of those, sanitize the binaries and make sure that all they're doing is writing to standard output, so we let them do.
So when you're saying that these NACL binaries only expose functionality via a well-defined API, so what does that API look like if it doesn't have a network?
Well,
So it prints to standard out and then I have to parse it?
yeah, and then we just read it. There's a server that takes the user code in, runs the tool chain to build the binary, executes the binary, and captures the standard output and returns that back. And so the system calls that a NACL binary can make, there's actually like a list of NACL system calls that include some networking stuff. All of it, they include a whole lot of stuff for interacting with web browsers and so on, because it's designed for the web browser, but we only permit like a very small subset of those.
But let's assume I want to build a web service that want access to local file systems, for example. So just something that takes some input and produces some output. So just to make it safe.
Well, the Go NACL toolchain doesn't permit any kind of networking or file system access. Instead, it actually gives you the ability to put in a fake file system in the form of a zip file, or you have a fake networking stack, so you can write a program that listens on localhost and connects to localhost and it will work. But that all happens in binary. So it's not designed to actually talk to the outside world in any kind of like complex way.
It then listens to a socket on localhost, or is it fake socket?
It's fake. It's totally in memory. It doesn't touch the kernel at all. And another thing that it does that's kind of nice is it will, if I put a sleep in there for 1 second and run that, it will actually do the sleeps, but it doesn't actually sleep on the server side. Instead, it pretends to sleep and advances a timer inside the binary and advances the clock. And when it's printing, it also prints the time at which this message should appear. And then that all gets sent to my browser in a sorry, you can just shout at me if this is boring, but I'll just put a couple of these in. So if I run this, it does 2 prints. If I look at my compile server output, it actually gives me this JSON object of events, and it has the delay to wait and then the message to print. And on the client side, I actually do the sleeps and replay the output as it should have appeared. And it's kind of a crazy machine for doing it, but it works. And if you with the NACL toolchain in 1.3, all this stuff will be available. So if you want to run a similar kind of service, you can. So one example of how this NACL toolchain might be useful is if you have something like, I think like we have Bigtable that has the notion of code processors where you can do queries on data and you can actually ship a program to the database server to perform some computation on the data before sending it out. And so I think MongoDB has a similar kind of concept. And you could use the native client port to compile, like if you run a database, you could allow people to write programs that you run locally against that data without having to expose any of your system to them. So that's how that could be useful.
So I assume this could also be very interesting for the app engine guys.
Sure, absolutely. There's also some other operating system ports. So the native client thing counts as an operating system as far as Go is concerned. There's a port to Sonos or Solaris. I think they're the same thing. I don't know. It's a work in progress. It looks like it's going to happen for 1.3. Dragonfly BSD is done, but the person who did it just kind of disappeared, and so there's no maintainer. If you are a fan of Dragonfly and want to be the maintainer of it, then please let us know. Otherwise, it will be removed. People are still working on the Plan 9 port after X years.
Why not?
Yeah, I don't know.
Good research.
Yeah, it's a good research project getting it to work. And there's also some movement towards getting Darwin ARM, which is this, and Android ARM working with Go. So I think there's still some way to go there, but there's a path towards making that happen, which is really cool. There are some changes to the Go command to make it more efficient. So if you run something like Go build or Go test, it currently needs to walk all of your sources, all the dependencies, and check whether any of them have changed. And that's a lot of files to read, a lot of files to stat and directories to list and so on. And it ends up being quite a large chunk of total build time. I think it's the second biggest thing apart from linking. So there's a proposed Go background command that starts a daemon that just watches your source tree and uses something like iNotify or whatever to wait for changes in the file system. And then it keeps the map of dependencies and modified times and so on in memory. And so when you run something like Go test, it can just ask the daemon, hey, what's the state? And not have to hit the file system every time. And we think that will dramatically improve things. And a side effect of that is that we'll finally take some of the various file system notification packages that exist for Go and bring it into the standard library. So there will be a single canonical cross-platform file system notification package in the standard library. And there is a interface for discussion available in this CL, if you can remember it. Think fast. We hope that 1.3 will include support for linking against Objective-C code. So for those of you who don't know, there's a tool in this toolchain called CGO that lets you write a small C program inside a Go source file, and you can link against C code in that way. And so you build like a little Go wrapper around the C code. And in the previous release, we made some changes to make it possible to do that with C++ code as well. But you still need to write a little C bridge into the C++ code. And there are some other small changes that we need to make it possible to link against Objective-C. And one of the really nice things is you can get native OS X apps going that way. And actually I was at a conference in Japan about 6 months ago, and there was a guy who demonstrated doing exactly that. And it was really cool because he just had native Cocoa widgets and so on that were all driven from his Go program. So I hope that happens. There is an issue that Rob Pike has said must be resolved for 1.3, which is the size of binaries. He ran a little test against 3 previous major revisions and saw that the binary size of Hello World almost doubled. And the reason for that is that people keep putting debugging symbols into the binaries for various different tools to read, and they're all slightly different, and there's no real reason they should all be different, or there's a lot of duplication there. And so We hope to fix that as part of some work that we're doing on the linker this round. And speaking of the linker, there is a whole linker overhaul planned for 1.3, and this is already, a lot of the heavy lifting here has already been done. So the GC toolchain, as we call it, stands for Go compiler. It's a clever name. It's a bit unconventional. It's actually the Plan 9 compiler toolchain, the C compiler toolchain, but repurposed for us. But the way it works is a little bit unusual. The compilers don't emit machine code like, say, GCC does. It doesn't give you an object file that is actual machine code. Instead, it emits an intermediate kind of assembly language that's these pseudo instructions, and the linker then translates that into machine code. So the Go linker at the moment does a lot more work than the average linker needs to. It does this whole translation process. And if you think about compiling a program, it's usually many packages, and all of those packages, dependencies notwithstanding, can be compiled in parallel. But linking must happen in serial, largely. You need to just reel the packages in and then clump them all together, do all the relocations and so on. And so the linker has become the main bottleneck in building programs. And so we want to improve that. So if we just look at what the current linker does, the Go compiler, our C compiler, and the assembler each produce this same intermediate assembly object format. And so you have many object files. The linker reads them in, it generates the machine code, and then it does your dead code elimination and moving things around and so on. And then it will emit the executable binary. But what we've done is extracted this part of the linker into a library called liblink, and we've put that code into the compiler. So now more work is being done here, where it can be parallelized, and less work is done in the linker here. And one really nice side effect of this is the linker is now a much simpler program. The hard part was actually the code generation. And so now that the linker is a simpler program, and it's a C program, by the way, now that it's a simple C program, we can actually rewrite it in Go instead. And once it's in Go, we can use all of Go's concurrency support to actually parallelize all the parts of it that we can. And so we're hoping that in Go 1.3, the linker will be significantly faster, which should lead to way faster compiles. And that brings me to the largest chunk of work that is kind of starting and underway for Go 1.3 and beyond, which is a transition of the Go compiler from being written in C to being written in Go. So as I mentioned, the toolchain is based on the Plan 9 C compilers. That was a great choice when we started. We took the assemblers and C compiler and linker wholesale, and then we wrote a new Go compiler in C, which was all a new program, but it used the same formats and conventions as the Plan 9 toolchain. And at the time, it was a great move because Go didn't exist in the first place. And then once Go did exist, it was changing all the time. And so I've never done it, but I'm told that working on a new language in a bootstrapped environment where your compiler is written in that language, it's really, really hard to make changes to the language because you need to modify the compiler and then have some kind of weird halfway modified version of the compiler that can compile the old one, and it makes my head hurt just thinking about it. It was just, it would have been difficult in the first place. And we did make changes a lot, so it would have really slowed us down. But today, these things aren't concerns anymore. Go does exist, and as of Go 1, it is stable, and so it's irrelevant. Instead, we prefer to use it in Go, because Go is just a better language, it's easier to write and debug. If we didn't think it was a better language, we obviously wouldn't be doing it in the first place. And Go has all of these tools, better support for modularity, and probably the most important thing, apart from Go being fun, is that by having a compiler written in Go, it means it's more likely that Go programmers will want to contribute to the compiler. At the moment, it's a C code. It's Plan 9 C code, so it's not the C code that most people are used to, and it's written with certain conventions and so on. And it was written by Ken and Ross, who are brilliant, but also have a kind of semi-inscrutable style. So, you know, they can read each other's code, but I think nobody else can read theirs. That's not true, that's unfair. But it's a half truth. So this is a really good thing. And so how are we going to do it? What's the plan? We're not going to rewrite it. Instead, we're going to translate the existing compilers into Go. And we're not going to do it by hand. We're going to write a translator to translate that C code into Go code. We're going to start the process in 1.3, but it will likely continue probably over the next couple of releases. And it's going to happen in 5 phases. First, we develop and debug the translator. And one really nice property of this is that we can continue to work on the compilers in parallel to developing the translator. And once the translator is ready, we can actually push the button and translate the C code to Go. And then we can check in the Go code and delete the C code. And at that point, we start working on the new Go versions of the compilers instead. The next phase is just to clean up, document, add unit tests and so on to make sure the code is all nice and solid and well understood. And then in stage 4, we use our profiling tools to optimize the code. And we can split the code into packages, refactor and so on. So now it's well tested. We can play with it more and make it an idiomatic Go program, not just a C program written in Go. And then the final step is to replace the front end with our packages that we already have written in Go for reading Go code and understanding Go code. And in the process, we may redesign those packages based on our experience with the compiler itself. And just a word about how we're going to manage the bootstrapping aspect of this. So if we distribute the source, how are we going to compile it? The idea is that the Go 1.3 compiler can be compiled with Go 1.2, and then 1.4 can be compiled with 1.3, and so on. And so you can imagine you would have a shell script that would automatically build each revision of the code based on the previous stable revision. And you would only need to bootstrap once per machine. So you're only going to build the 1.2 compiler once, and so on. And so that whole process can be pretty much automated. But as somebody already mentioned to me this evening, it scales poorly over time. So one solution to that is to write a backend for the compiler that emits C code. It doesn't need to be fast, it just needs to be correct. And then we can check that C code into the repository, and so you just need a C compiler to bootstrap the compilation process. And so there were a bunch of things we could have done, and I'll just address why we chose to do them the way we did. There was quite a bit of, there were some people that really wanted to write compilers from scratch, but we rejected that approach because the compilers that we have are really well tested, and they handle many subtle cases in the language really well. I'm actually told that Go is a pretty difficult language to implement, more so than others, just because of interesting corner cases in the specification. And so we've actually invested more than 10 man-years of effort in the compiler, so it would be a bit foolish to just throw all that away. Why not translate manually? Well, who wants to do that? I don't want to do that. I don't know anyone who wants to do that. People suggested maybe we should translate and connect the Go packages for parsing and manipulating the tree immediately. But I think there's too much of an impedance mismatch between the existing compilers and those Go packages for that to be really smooth. And another option, of course, is just to discard the compilers that we have and put our emphasis on GCC Go, which is a Go front end for GCC. Or even there is a project called LLGo for building a Go front end for LLVM. And really, it was felt that the current compilers are a large part of the flexibility that we have as a project. and like tying our development process to the development process of these really large C and C++ programs seems to really defeat the purpose of what we're trying to achieve here. And so finally, as with previous releases, we're going to see a really long tail of small fixes and changes and things that we didn't expect would make it in. And so you'll have to wait and see what happens there. And so I've gone over time. That's my list of things. Thank you very much. I'm also happy to answer any questions. Yeah.
The ARM platforms, is this a native support that is being built?
Yeah, yeah.
No
So,
cross-compiler?
sorry.
No cross-compiler needed?
No, there is cross-compiling. I mean, you can run the toolchain on the ARM platforms.
Okay.
You can also build ARM code from other platforms. So the Go toolchain is actually really nice with cross-compilation. You just set some environment variables, and you can build targeting any of the systems that we support. So it's really easy to build a program and then copy it to your phone and run it there.
Including the Go tool itself?
Yes. Yeah. In fact, we don't provide binary distributions for them, but there are some community-provided binary versions of the ARM toolchain, which people run on Panda boards and other development platforms.
Question concerning the Go daemon for the Go tools. How does it interact with the Go path? Because it's just an environment variable, you can set any time and change any time.
Yeah.
And how does the Go daemon notice which files?
I would presume that the Go background daemon would read the value of Go path at startup, and that's the one it would use.
And if you change it after that, will affect
Well, or you could imagine the client sending it.
Yeah, the client could send it, that's true. I mean, it hasn't been implemented, so if this is a concern, you should watch the development and, it's definitely worth thinking about.
Do you ever use naked return statements?
Naked returns.
Yeah.
I try not to, because they tend to not be worth it. Yeah.
Regarding the native client support, what is the reason to target Pinnacle?
So Pinnacle is it's a intermediate format that's very tied to LLVM. So it's actually what the new versions of NACL are using, which is it means that you compile your program to this Pinnacle format, and then on the fly, the browser will compile that program to whatever architecture you're on. So if you're on like ARM 386 or whatever, it will do that compilation in the browser. And the reason why we didn't target that with the toolchain, instead opting to just produce the native machine code, is the Pinnacle format is not very well defined. It's basically, whatever LLVM reads in. And so it would be really hard for us to build a toolchain that would emit that code, and as the project changes, we would have to constantly track that. And we previously had a version of native client in the tree, but we found that they kept changing the format so often that it just kept breaking, and we didn't have the manpower to follow
It is locked down and frozen now.
It is, yeah, it is now. Yeah.
But I think the real reason is that it's so different from what the existing compilers produced. It was a very small change to make NACL x86, but changing Pinnacle will be a whole new world of compiler.
So it is a translated compiler with a sort of machine translation. Are you basically trading Ken's rather unreadable code of a machine-generated unreadable code?
Yeah, I mean, I expect the Go version of the C programs will be pretty difficult, but not much more difficult than the existing C code. But it would be much easier to refactor and so on.
With Go 1.3 and 1.4, we are still maintaining the GCC Go.
Absolutely, the development of GCC Go continues and will continue. So at Google, in our build system at Google, you can flip a flag and build with GCC Go. And we run all of our tests and everything with GCC Go as well as GC, and we're committed to maintaining parity with GCC Go. All right, I might we'll have a break.
Yeah.
And then
We have a short break. I suppose we have 5-10 minutes break. Then we'll continue with the second speaker. Right? Thank you.
thanks.